So the goal here is to show that an implication and its reciprocal is an equivalence. And a more mathematical way of stating this is to show that P implies Q and its reciprocal, so this is the implication. So the implication, and this is its reciprocal. So the reciprocal is also an implication, but by switching the order of the two statements. So P implies Q and Q implies P, and P is equivalent to Q have the same truth tables. So the way we're going to approach this is by first starting out with all the possible combinations of truth values of P and Q. So we have true, true, false, and false, and then we're going to have true, false, true, false. So that's all the possible combinations of truth values of P and Q. Now we're going to first start with the first implication. So P implies Q. Remember, the truth table for this is true, false, true, true. Then we're going to write up the reciprocal. So Q implies P. Remember, an implication is only false when you start from a true statement and you imply a falsehood. So for the reciprocal, we should pay attention to this line, okay? Because it's this line that says we start from something that's true and imply a falsehood. So we're going to have true, true, false, and true, like so. We can combine our two implications. So P implies Q and Q implies P. So here we want to look at our two tables for our two implications, and this entire thing, this entire and statement, is going to be true when both of those implications are true at the same time. So we have true, true, that's true. We have false, false, true, so that's false. We have true, false, that's false. And then we have true and true. Now remember, P is equivalent to Q, has the truth table true, false, false, true. So we have effectively the same truth table for those two statements. This is very important because when you're going to prove that that two statements are equivalent, you can resort to proving two things. So you can dissect it into two proofs of P implies Q and Q implies P. Let me give you an example. Let's say you have the statement P, which is the function is bijective. You don't need to know what a bijection is here. That's not the point. So the function is, or let's say actually, the function f is bijective, and Q is going to be the statement, the function f is invertible. Now, at some point, we're going to prove that P is equivalent to Q. So let's say eventually we will show that P is equivalent to Q by showing that P implies Q and Q implies P. So if a function is bijective, then it is invertible, and if a function is invertible, then it is bijective. I'll leave it at that for this video. Take it easy and enjoy yourselves.